Okay, welcome everybody. So today we're going to be talking about a very important law. Today we're going to be talking about Dalton's Law of partial pressure. Now Dalton's Law usually is used in conjunction with other gas laws. And the reason Dalton's Law is so important is that it allows us to do calculations regarding mixtures of gases. So Dalton's Law states that for a mixture of gases in a container, the total pressure exerted is the sum of the pressures each gas would exert if it were alone. So basically, the individual pressure of each gas can be added together to get the total pressure of the mixture. So the pressure of the total mixture is equal to the partial pressure. So pressure 1 plus pressure 2 plus pressure 3, and each of these would be a different gas. Depending on how many different gases are in the mixture, that'll tell you how many things you're adding together. Now, this is related to moles as well. So moles, just like pressure, is an extensive property. And so what we can do is similarly, the sum of the moles is going to be the total number of moles. So you'll notice that a lot of times we can use either moles or pressure to do these calculations. Okay, so down here we have an example problem. We have 46 liters of hydrogen gas and 12 liters of oxygen gas, each of which are at 25 degrees Celsius and 1 atmosphere, are pumped together into a 5-liter tank. Question is, what's the total pressure at 25 degrees Celsius? So this is kind of a tough question. What's happening here is you have these gases that are going to be put together in a 5-liter tank. We are changing the volume of these gases. So for the hydrogen, it's going from 46 liters to 5 liters, okay? It's gonna stay at the same temperature, but of course this is gonna change the pressure in the tank. So notice that the temperature is not changing, but the pressure is. And so first thing we can do is we can use Boyle's law to figure out the new pressure of the hydrogen when it goes into the 5-liter tank. So it's P1V1 equals P2V2. So for hydrogen, our initial pressure is 1 atm. Our initial volume is 46 liters. We don't know the new pressure, but we do know that it's going into a 5-liter tank. Okay? So if we do the math on that really quickly, it's going to end up being 46 divided by 5. And so for hydrogen, the new pressure of the hydrogen gas is going to be 9.2 atmospheres. Okay, we can do the same thing for the oxygen gas. We could take our initial pressure, 1 atm, and our initial volume, which was 12 liters, and determine the new pressure at 5 liters. So this is going to be 12 divided by 5, and so we end up with 2.4 atm as the new pressure. Now, this is the individual pressure of the hydrogen, and this is the individual pressure of the oxygen. If we want to know the pressure of the mixture in this 5-liter tank at 25 degrees Celsius, all we have to do is add together the pressures of the individual gases. And so P total is going to be 9.2 plus 2.4, which is going to be 11.6. Okay, so again, we use Dalton's law in conjunction with other gas laws. In this case, I needed to calculate the change in pressure using Boyle's law, and then I had to add together my new pressures to get the total pressure of the mixture. Another really important thing that we can use, knowing that the total is a sum of the partial pressures of these things, or the total is the sum of the moles of each individual component of a mixture, we can actually determine a mole ratio, and so or a mole fraction. Okay, so it's a ratio of moles of a component to a total number of moles in the mixture. I honestly don't remember the symbol for this. We'll come back to that. It's usually expressed as a decimal value. So it's not actually given as a fraction, okay? Again, though, it's calculated by taking the moles of, gas X, whatever it is, and dividing it by the total moles of the gas mixture. It's a lot like percentage. It's like the part that's made up of one gas divided by the total number of moles of the mixture. It's just that we're not going to multiply it by 100 at the end. So it's expressed as a decimal value. We keep it as a decimal because often it's used to determine the amount of a mixture that is made up of a component. So we often use it to multiply. Here you go. We can see a couple of problems here. So it says to calculate the mole fraction of oxygen when the partial pressure of oxygen is 156 torr and the total pressure of the mixture is 743 torr. So this is about as easy as it gets. I have the partial pressure here. I have the total pressure of the mixture here. So to get the mole fraction, it's going to be 156 over 743. Now make sure that they're the same unit. So if you're given a partial pressure in ATM and the total pressure is given to you in torr, one of them has to be converted. So they need to be the same unit. In this case, they were both torr, so it's fine. We're simply going to divide. So it's going to be 156 divided by 743. And so I get about 0.210. And so that would be my mole fraction. I would leave it as a decimal value. And here's a reason why. We can do problems like this using the mole fraction. So it says that the mole fraction of nitrogen in the air is 0.7808. So that means roughly 78% of the air around you is nitrogen. It says to calculate the partial pressure of nitrogen in a 760 torr sample of air. So I want to know, out of the total pressure, how much of it is the partial pressure of nitrogen. And this is pretty simple. If I know that about 78.08% of it, or the mole fraction is 0.7808, is nitrogen, then I can simply multiply the mole fraction times the total, and I can get the partial pressure. So again, I can take my mole fraction, 0.7808, okay, and I can multiply that by the total, 760. And what I'll get when I multiply this product will end up being the partial pressure of nitrogen. So 0.7808 times 760 gives me about 593 torr. So that would be the partial pressure of nitrogen in the air. So one more time, if you have a total already and you have a mole fraction, you can multiply them to figure out the partial pressure, okay? That means roughly, if I take 760, my original amount, and subtract the 593, that's nitrogen, roughly 167 torr is the other gases that are in the air. So the rest of the 760 would be made up of other gases. But the partial pressure of nitrogen right here would be 593, and again, we found that by multiplying here. By the way, I think I remember this, the symbol. I want to say that it's a chi. I want to say it's like a funky X looking thing. Not sure, you might want to check the book on that. But I think that's going to be the symbol for the mole fraction. Okay, I know that it's found mathematically by taking the moles of the single gas, the individual gas, and dividing it by the total. And again, I also know that it's most often used to multiply against a total to find the partial pressure of a single gas. So keep these things in mind when you guys are working on your problems, and good luck.